Acceleration is a very big concept when it comes to motion. Finding the average acceleration is quite simple. If we want the average acceleration, we just sort of have to think about the definition of acceleration itself. It's a change in velocity over time, or the rate at which we are changing our velocity. You think about this as delta v over delta t. Remember, delta means change. So this is a change in velocity and a change in time. Now, whenever we have a change, we always do final minus initial. So we do final velocity minus initial velocity, and final time minus initial time. Now, another big concept in motion are what are called DVATs, or DVATs. Sometimes you might hear me call them those. And these are our 4 big equations that will help us solve almost any motion problem in physics. So our first one stems from this average acceleration definition. We arrange things around a little bit, and we get that our final velocity is equal to our initial velocity plus a times t. I go through the algebraic rearrangement in my average acceleration example video, so check that out if you are interested in how I got from this equation to this equation. Now our other 3 are, this first one is the final position is equal to initial position plus a velocity times time, and that comes from our average velocity equation. And then, watch carefully now, this next one is pretty tricky, but it is one of our more useful forms. Our final position can be equal to our initial position plus our initial velocity times the time plus 1/2 your acceleration time squared. And then our fourth and final one is a final velocity squared is equal to the initial velocity squared plus 2a times our change in position. Now these are what we call our big 4. Our big 4 or our DVATs. Now DVAT stands for distance, velocity, acceleration, and time, or displacement, distance or displacement, depending on the situation. Now what's great about these 4 formulas is that they can pretty much help us solve any motion problem in physics. Now if you're interested in seeing how these are derived, please ask me in class, and I can point you to some really good websites that go through the derivation. Some of them are more clear than others. For example, these 2 stem from our average acceleration and velocity equations, while others are more complicated. This very long one down here, while it is very useful, comes from an experiment Galileo did a very long time ago. But it's a really interesting derivation. If you would like to see it, please let me know. Now, we can solve a lot of different types of motion equations. When we get to projectiles, we'll be doing this in 2 dimensions, but for now I just want to stick with the 1 dimension. So when we have motion problems, the best thing to do is to follow that goal method with your knowns and your unknowns. Look at the knowns that you have, and then try to figure out which one of these 4 equations best fits your needs. So I'm going to do an example of that now. Please excuse my messy handwriting. Here it is. So a babysitter pushing a stroller starts at rest and accelerates at a rate of 0.5 meters per second squared. What is the velocity of the stroller after it has traveled 4.75 meters? So with our goal method, we want to list our knowns and our unknowns first. So let's take this one at a time. A stroller starts at rest. That's a key word. If we're resting, what are we doing? We're not moving. It's sort of like we're standing still or we're stationary. So you can think about a babysitter starting at rest, or she's standing still. So this lets us know our initial velocity. Our initial velocity is going to be 0. I'm going to leave the units as meters per second. I get that from our acceleration, which is our next thing, acceleration. Our acceleration is 0.5 meters per second squared. because I have meters per second squared, I wanted to leave my velocity as meters per second. So we're at rest, start at 0 meters per second, we're accelerating, and then what is the velocity? So this is the velocity of the stroller after it has traveled 4.75 meters. Okay, meters, that's a distance or a displacement. So we're going to put this as x. So this is going to be x final. This is where we end up. But if we started off at, I don't know, x equals 0, start off at equals 0, if we just did a change of x, then this value would also be our change in x. Then, what is the problem asking for? What is the velocity of the stroller after it has traveled that distance? So, the velocity, we're looking for a final velocity. Once again, with the goal method, we're going to assume our units, and we're going to assume that they're the same as our initial velocity. Okay. So, we have an initial velocity, we have an acceleration, and we have a change in position, and we are looking for that final velocity. So having our knowns, we're going to go back and look at our DVATs to see which will fit the equation best. So we can go through this first equation. So we want to solve a final velocity, so that looks good. We have an initial, we have an acceleration, but we don't have a time, so we can't use this one. This one would be if we were moving at a constant velocity, but also we don't have time, so we couldn't use this. Then we have here, change in position looks good, initial position, oh, but there's time again, so we can't use that. So we need to go to our fourth and only equation that does not involve time. And if you look closely, you'll see that we have every component in order to solve this problem. We have an initial velocity of 0, we have an acceleration, 0.5, and we have that change in position to be 4.75, and we are solving for that final velocity. So everything checks out. So that's our formula. The final velocity squared equals to the initial velocity squared plus 2 times acceleration times delta x. Okay. So this is our problem now. We solve for our unknown in terms of our known, so we're just going to take the square root of this whole thing, and we plug in our numbers. We have 0 squared, which is easy, plus our 2 times our acceleration times our change in position. Now, because this value is 0, you didn't have to write the 0 out. You could have just crossed it off and said that the 0, just like so. You don't have to plug that value in to receive full credit, but as long as you understand that you are crossing it off because it is a value of 0. And then after we plug this into a calculator, we get that our final velocity is equal to 2.18 meters per second. Now, if you remember, think back to your favorite middle school math teacher, that when we have a square root, that this can be either positive or negative. But how do we decide which is which? Well, this is when drawing that picture at the beginning comes in handy. So if we draw our babysitter, and she's going to push the stroller this way, it helps to define what our positive direction is. So if you think of a coordinate plane where this is x positive, she's moving in the positive direction. Now, of course, you could have defined positive as any other way, but letting me know that this is your positive direction and moving this way, we can confidently say that this will be positive 2.18 meters per second. Now, if you had told me that this was the positive way, if you had told me that this was positive, and our babysitter was walking this way instead, our answer would have been negative 2.18 meters per second. Either would have been valid, but defining your position at the beginning with your pictures helps clear up any confusion towards the end of the problem. So either would be an acceptable answer. You just have to let me know and to communicate which is positive and which is negative.